Hello everyone, I will be talking about our study, a super resolution based approach for HTTP adaptive streaming for mobile devices. My name is Ekrem Çetinkaya. I'm a PhD researcher in the ATHENA laboratory in Austria. And let's just jump in. So I will start with some numbers to clarify why we chose to work with mobile devices. When we see the YouTube watch time, actually 70% of it is coming from mobile devices. But on the other hand, 26% of smartphone users reported that they encounter a video streaming problem every single day. So we thought we can address this QoE issue using the hardware capabilities of the mobile devices. And in fact, when we check them, like you can see the ML benchmark GPU scores on the screen. You can see over the 6 years, the ML execution power is actually more than tripled. So we thought this is a power that we can utilize. And the approach we thought would be suitable here is obviously the super resolution. We can define it as the increasing the spatial resolution of the input and trying to make it as lossless as possible. We have traditional approaches like bilinear upscaling. I mean, they can produce some results, but of course we have to use like artifacts that we don't want to get rid of. And in fact, in the recent years, we had this nice improvement in the deep neural network-based super resolution approaches. They can tackle this problem, but of course they take a lot of time to run on the hardware because they are very complex. So we saw the potential in the mobile devices and the potential in the deep neural network-based super resolution approaches. That's why we proposed something to address this. We actually proposed two components here. The first one is the SR-ABR network, which is a lightweight super resolution network that considers the limitations of the mobile environment. And also we propose an ABR algorithm that can work with the super resolution because current ones cannot do that. So which SR? That's an ABR algorithm that considers the throughput cost, buffer cost, and the third component we have is the quality cost, which is the ABR that we use to utilize the super resolution on the mobile devices. So let's just jump into the system's architecture. We will have the brief architecture here. So the SR-ABR, what we did was a standalone Android application. And the first time the application launches, it just collects the device information and sends the server a request to asking for the set of SR networks. Then the server sends back the suitable SR networks to the client, and then these deep neural networks are stored on the client side, and they will be used on the upcoming playback sessions. And during the playback, the SR-ABR algorithm collects the ABR-related information, like the buffer network and device status, and then sends a request. Now here it has three options basically. It can ask for a high-resolution segment, just directly plays it, or asks for a low resolution segment and directly plays it. The third option is when the super resolution comes into the play. Here it asks for the low resolution segment. Then, before playback, the super resolution networks upscale the segment to the higher resolution, then the playback starts. Doing this actually reduces the bandwidth we use to get the high resolution segment from the client, server. Sorry. So the SR-ABR network we use, as I said before, it's a lightweight structure because we need to make it sure that it is running on real time on the mobile device. So what we did was we just passed it on the convolution and ReLU block the first time, and then we do it again. Then here we have these additional layers. These just gets the output from the previous layers and add them to the output of the current layer. And by doing so, we actually exploit the information from the previous layers more than once, and this enables us to actually exploit the information using very fewer layers compared to the rest, doing them straightforward. And we repeat the structures 2 more times actually, and then at the end, like this output from the first layer is actually used twice, 3 times in the network. Once we do that, we add a clipped ReLU activation function at the end because we need to do some quantization to make the network run on the mobile device. And this clipped ReLU, just limiting the numbers between 0 and 1 is actually helpful during the quantization process and doesn't lose that much of accuracy anyways. And at the end, we just use the pixel shuffle layer to increase the resolution and we get the high resolution frame. So this is the structure we use for our deep neural network. So for the ABR algorithm, we start with some observations here. Let's say we just request a high bitrate segment from the server. This actually causes 3 things. It causes us to transfer more data, which results with a higher throughput cost. And also, it takes more time to download this, so it results with a higher buffer cost. But on the other hand, we get a higher quality segment, and that is just lowering the quality cost on the ABR algorithm. Let's just see a scenario here. Let's say we have 3 different resolutions from the server. And if we check their throughput cost, the high resolution segments have a higher throughput cost, and the same applies for the buffer cost. But contrary, for the quality cost, the low resolution segments will have a higher quality cost. So then in this scenario, the ABR algorithm will choose the middle quality, like 720p segment. But things change when the super resolution comes into the play. When we do that, we can actually lower the quality cost of the low resolution segments because they can be upscaled using the deep neural network on the client side and without losing that much of quality. In this scenario, the ABR actually can choose the low resolution segment. So what we achieved was we reduced the bandwidth without hurting the quality cost that much. So what is the ABR algorithm we use? We have 3 different cost functions here. The first one is throughput cost, which is basically current bitrate of the over the estimated throughput. This is the formulation. The second cost we have is the buffer cost, which is the download time of the current segment divided over the current buffer level minus the low threshold of the buffer. These are just pretty straightforward. And then we have the quality cost. This is actually composed of 2 components. One is the distortion penalty. The second one is the instability penalty. Distortion is how much quality we lose compared to the request in the highest quality segment. And this instability is how much quality we lose compared to the average quality we got throughout the playback. This is the formulation. Here, how we define quality changes based on if we use the super resolution or not. If we don't use the super resolution, the quality is basically the current bitrate level divided over the maximum bitrate we can get from the server. And if we use the super resolution, the quality is just improvement in the quality we get using the super resolution network on the client side. So combining these 3, throughput cost, buffer cost, and quality cost in a weighted manner gives us the wish SR-ABR algorithm. And we can see the formulation here. These alpha, beta, and gamma values are predefined. You can change them based on your needs, but we use the same values as we did in our previous paper, wish ABR algorithm. So let's jump to the evaluation. For experiments, our testbed was just basically an ThinkPad running on Ubuntu. For the mobile device, we went with Xiaomi Mi 11 because at that time, Snapdragon 888 was the latest state SoC for us. It was running Android 11, and we used Google's Xor player for implementation. For the network status, we used Linux traffic control basically, and we used an existing 4G network trace, and you can see the statistics about the networks we used here on the screen. For the videos, we went for 4 different videos, and we tried to include as many different characteristics as possible. Like here, for example, gameplay is just purely computer-generated content. The Rela is just natural capture content, and Tears of Steel is just a mix of it. Also, we wanted to go with different SI-TI values because of the video characteristics. And you can see like the gameplay has high SI, low TI, Rela has low SI, high TI, etc. To prepare them, we use the HEVC as the codec, and then we choose segment duration as the 4 seconds. The corresponding bitrate ladder and their corresponding resolutions are given on the screen. To compare with the other ABRs, we chose 4 of them. It's BBA0, default ABR algorithm in Xor player, Squad, and Wish. For the super resolution network training, we use the div2k dataset, which is basically images in low resolution and high resolution. But also we extracted frames around 100 videos from different datasets, and then we prepared them with HEVC. Here we chose our target resolution as 1080p, and we have different upscaling networks for different upscaling factors. Like let's say if we have this 270p as the input, our network has upscaling for 4 times, 360p 3 times, and 540p 2 times. For training and comparison, we compare our SR-ABR network with the Ekrem, which is one of the latest state-of-the-art deep neural networks that can be run on the mobile environment. Both networks train on the div2k dataset, but we also fine-tuned them on the encoded frames to make them more robust against the encoding artifacts. Training setup was same for both of them. We just used the Adam optimizer, we applied learning rate scheduler, and used MSE as the loss function. To implementation, we used TensorFlow Lite on the mobile site, and also we applied float 16 quantization to make them run faster on the mobile GPUs. For metrics, we have basically 5 of them. Average bit rate, number of stalls, and the stall duration, the QoE score based on the IQ and TP1203 extension mode 0, VMAF for the visual quality and also VMAF over bitrate to get an idea about how much quality we get over a delivered per kilobit per second. I just forgot to include the metrics here, sorry about that. Results. Let's start with the super resolution networks. We used MoviDNN application to evaluate them. Here we can see the execution speed of super SR-ABR network and the Karnam. SR-ABR network just manages to run in real time in all different upscaling factors. Of course, the higher the input size is, the lower the execution time. But still, we managed to make it run time. When we check VMAF, Karnam performs better here in all scales, but the difference is not that much. But the important thing here is just both networks achieve a quite significant improvement over the bilinear upscaling, which is, as we know, the default upscaling algorithm in the Android. So for the ABR results, which SR here uses the least amount of data, as it has the lowest average bitrate. And when it comes to the stall events, here again we experience no stall events in the WISH SR-ABR algorithm. And when we check the QE score, we actually get the highest QE score here, and we just use the ITP1203. I mean, it's important to note that this QE metric doesn't take account into the visual quality, so that's why we also had to examine the VMAF scores achieved overall. I mean, here the WISH SR falls back a bit because, I mean, obviously BBA gets the highest VMAF because it uses the highest amount of data. But we also see this VMAF over bitrate, which is like how much of VMAF score we get per delivered kilobit data. And when we examine that, actually WISH SR gets the highest quality. So meaning that it's just used the best quality per delivered data. To conclude, we propose two things: the SR-ABR network, which is a lightweight SR-DNN that considers the limitations of the mobile environment. It can achieve significant improvement over the default upscaling factor in the Android. And also we propose an ABR algorithm that can work with the super resolution approaches, which is a weighted sum model of throughput cost, buffer cost, and quality cost. And combining these two, we get the SR-ABR scheme. This achieves a significant data reduction up to 43% compared to the other ABRs, while providing the high quality of experience. Thank you. That's all from my side. If you have any questions, you can reach us via one of these channels as well after the presentation. And thank you.
Do we have any questions for Ekrem? Oh, Thomas.
I'm just checking, because I know that we have a team that does a lot of work on display management and so on and so on. So if you say this Android bilinear interpolation, is this the only way that you can do upscaling in the device? Because I believe if you take like a Snapdragon 888 as you do, there should be better ways to do upscaling. I mean, we have AI processing in our displays as well. So I'm wondering why you do this in software and not use the native functionalities of the device.
Thank you. I mean, we just tried to be in the example layer, and there the default upscaling was the bilinear and it was done by the software. So we just compared it with that. But I'm sure that there, as you mentioned, there are better ways to do that. But here we just take a reference player for ourselves as we do in the research and then try to compare with that. But as you can see, this can be better implemented and better optimized for sure. But we are just doing the research here, so it's the first step for us.
So congratulations for the work, and I think it's very good that you look what the device can do. My only request, and this is not to you, but also to Alex, we need to have additional metric, which is the power. You can do great things, but if you can't use your phone after you watch your video, please put additional color.